So, welcome everyone. In today's session, I will be discussing with the concept of root locus. Hello everyone, I am Mr. Ninath Kulkarni, working as an assistant professor in Department of Mechanical Engineering at Walchand Institute of Technology, Solapur. In today's session, I will be discussing on the concept of root locus. At the end of this session, the students will be able to learn the basics of the root locus method. So, what do you mean by root locus? The closed loop poles that we have found out by using the transfer function, if some parameter is varied of the system, how these closed loop poles move in the S plane, that we have to know, because the knowledge of this movement of closed loop poles with small changes in the parameters of the system, it helps in the design of any closed loop system. So, once we know how these closed loop poles move, we should understand the stability of the system. That helps in this, determining the stability of the system, in which area it is stable, in which area it is unstable. So, such movement of poles can be determined by root locus method. This method was introduced by W.R. Evans in 1948. So, it is a graphical method in which movement of poles in the S plane is sketched when a particular parameter of the system is varied from 0 to infinity. So, we vary some parameter like controller gain from 0 to infinity, and we sketch the movement of poles in the S plane when this parameter is varied from 0 to infinity. So, this is a closed loop system. The input is R of S, that is Laplace transform of input, and the output is C of S. This is the transfer function with the controller gain K that we are going to vary from 0 to infinity, and this is the feedback taken from the output in terms of H of S. So, the characteristic equation obtained is 1 plus G of S into H of S equal to 0. So, for a closed loop system, we can obtain a closed loop system, we can obtain a characteristic equation, that is 1 plus G of S into H of S equal to 0. Now, if we go to previous slide, so G of S, it is a combination of this controller gain and G dash of S. That means we have to multiply this K block into G dash of S block to get the transfer function G of S. So, replacing G of S by K into G dash of S, we get 1 plus K into G dash of S into H of S equal to 0. So, once we vary this K from minus infinity to infinity, for each separate value of K, we get a set of locations of poles. So, these poles move with this parameter K that is varied from minus infinity to infinity. If we join all such locations of poles, the resulting locus is called as a root locus. So, consider a system with unity feedback with transfer function given by G of S is equal to K upon S into S plus 2. So, once we obtain the characteristic equation by using the equation that we have given in the previous slide. So, 1 plus G of S into H of S equal to 0. So, 1 plus this G of S into H of S is K upon S into S plus 2. So, once we multiply this S into S plus 2 by 1, so we get S square plus 2S plus K equal to 0. So, this is the equation that we get. Now, we will plot the poles, we will plot the location of poles if we vary the k from 0 to infinity. So for simple terms, we vary from 0 to 1, 2, 3, 4. Okay. So when k is equal to 0, so s square plus 2s plus k is equal to 0, s square plus 2s is equal to 0, that is s into s plus 2 equal to 0. So we get the value of poles as s equal to 0 and s equal to minus 2. So 0 we mark the pole by using this, and minus 2 we mark the pole using this. So once we keep the value of k as plus 1, so we get the equation as s square plus 2s plus 1 equal to 0. That is the quadratic equation, s plus 1 bracket square is equal to 0. So we get the values of poles as s equal to minus 1 and minus 1. So we mark the pole as here for k is equal to 2. So for k is equal to 0, we get one value, two values 0 and minus 2, and for k is equal to 1, we get minus 1. So minus 1 we get. Similarly, if k is equal to 2, we get s square plus 2s plus 2 equal to 0. So we get a complex root, that is minus 1 plus j1, that is minus 1 is the real part, j1 is the imaginary part, minus 1 minus j1, okay, that is denoted by this pole, minus 1 of real part, j1 of imaginary part, this is the pole 1, minus 1 of real part minus j1 of imaginary part, this is pole 2. So there are two conditions that value has to satisfy if it has to lie on the root locus. One is angle condition and another one is magnitude condition. So for a general closed loop system, the characteristic equation is given by 1 plus g of s into h of s equal to 0, or if we transfer 1 to the RHS, we get g of s into h of s is equal to minus 1. As the s plane is complex, we can write the above equation as g of s into h of s is equal to minus 1 is the real part and there is no imaginary part, so we can write as j0. So angle condition, what it states that the angle of g of s into h of s should be odd multiple of 180 degree. The angle should be a odd multiple of 180 degree, that is plus or minus 2q plus 1 into 180 degree for q is equal to 0, 1, 2 dot dot dot. Okay. So how many number of asymptotes are there? That is given by q. So the angle condition can be stated as angle of g of s h of s for any value of s, which is the root equation of 1 plus g of s into h of s equal to 0 is 2q plus 1 into 180 degree, where q is plus 0, 1, 2 and so on. So the angle of any value of s should be odd multiple of 180 degree, that is given by the angle condition. If this angle condition is satisfied, it should lie on the root locus. Similarly, if magnitudes of both the sides of equation are g of s into h of s is equal to minus 1 are equated, we get the magnitude of g of s into h of s is equal to magnitude of minus 1 minus j0 is equal to 1. So the magnitude condition says that the magnitude of this open loop equation, characteristic equation, g of s into h of s is equal to 1. It should be 1. Okay. So this is the magnitude condition. So a point should satisfy both the angle condition and magnitude condition. Once these conditions are satisfied, it must lie on the root locus. If not satisfied, it is out of the root locus. The references that we have considered is the control system book by U.A. Bakshi and V.U. Bakshi of Technical Publications of 5th revised edition in 2007. Also, the modern control engineering by K. Ogata, Apprentice Hall of India, Private Limited, New Delhi, 4th edition. So, once we know the poles and zeros of the system, we can determine the stability of the system. So, thank you.